Okay, so looks like we can start our discussion. Um, so I think I gave you until Monday to submit the answers. So if you have them ready now, go ahead and submit. If you don't, just make sure that you upload your answers by Monday. Um, so again, the idea with this case study is that you understand the importance of some of the concepts that are part of this profession, of this field, systems engineering. Um, so again, we're dealing with a very complex engineer system here, telescope that has a very precise goal, has to deliver a certain quality of images, and there's a lot of money put into this project. Sometimes we think that this doesn't necessarily affect us, but remember, these are government agencies. NASA is part of the government, and all the funding is coming from you, from us, the people who work. So it's actually having an impact on how that money is used and spent. Um, so let's look at the questions. So what was the goal of the Hubble? What was the goal? Anybody?
Get better looking pictures.
Yes.
Clear.
Yes. So we are looking at a telescope in space that will eliminate the atmospheric effects that blur images seen on Earth. Actually, they wanted to improve their current images, and they were getting 3 times, or they wanted to have 10 times the better quality of images. And what was the overall cost of this project back in 1970s, 80s? The initial cost 1.5 billion, so a lot of money, and then an operating cost of 200 million a year for 15 years. So an expected total cost of 5 billion. So we are dealing with a very massive use of resources here. A lot of money, and obviously after putting all those resources into this project, they wanted to see the results. But there was a problem. What was the problem with the Hubble?
The mirror was too far.
Yes. There was a problem with the mirrors. The Hubble was providing resolutions of 3 times that available with telescopes on the ground. But the originating requirement for the Hubble was being 10 times Earth-based telescope. So it was not delivering the actual goal. Is this something? Well, yes. If you're putting all this money into something, right? You want to get as close as possible to the goal. So 3 times looks like not a major difference to what they already had, and after putting $5 billion into this project, that was not enough. So how could this problem be avoided? I want to hear some answers here.
They could have tested them.
Yes. And why they didn't do it? What? Well, they were able to test the mirrors before the system went to space, right? That was the problem. They did some testing, but they didn't test the system together, right? So without testing the performance of the system as a whole, they were not 100% sure that the system were going to perform in space. So there was a cost associated when they interviewed the people in charge of performing the testing. They said that they performed all the tests that was required by NASA, but they never tested the system with all the components together. They said that the cost was too high. I think they mentioned that the cost was hundreds of millions of dollars. So my next question to you is, do you think the cost of preventing the problem was justified? Yes. Why?
They spend more fixing it.
Exactly. So again, that's the idea. When you apply systems engineering concepts and you are aware of the problems that can happen when you're dealing with these complex systems, you need to make sure that they are not just performing individually, the parts are not performing just individually, but at the same time that when you put the whole thing together, they're performing as expected. And part of making sure that that will happen is to perform the right tests, right? And by avoiding doing that, you're basically putting your system into a very high risk of not performing, and it will end up costing you more money at the end, as it happened for this particular case. So we are not just concerned about making sure that we get a good enough solution that is balancing all these performance measurements, but at the same time, we want to make sure that the system is performing as expected when you're putting them or when you're putting the system into the environment that it will work for the time expected. So any questions about this case study? Good. So let's try to get through the last two items for today, and then we are going to dismiss the class. So the next item is the systems engineering as a profession. So again, the goal of this lecture is to help you understand what are the differences, what are the things that we are looking for when we are studying in systems engineering. This area of engineering as a profession has not been widely recognized despite of increasing prevalence of complex systems and the essential role of systems engineering in development of systems. However, I can tell you that within the industrial engineering field, there's a movement into integrating systems engineering as part of the profession. So if you're familiar with, for example, the magazine for the IIE, if you're part of the IIE student organization, if you look at the magazine, they already have the systems component within the professional organization. It's called IISE now, not IIE. So there's a movement within our profession to integrate some of these areas in the industrial engineering field. Systems engineering primary recognition has come in companies specializing in development of large systems. So as I mentioned in the first lecture, if you have plans to work for these government organizations such as the military, the Army, the Marines, the Air Force, the Department of Defense, Department of Homeland Security, the NASA, all these companies have a lot of, they deal with very large projects and they implement a lot of systems engineering concepts within their engineering departments. Boeing also, and all these airplane manufacturers implement a lot of systems engineering within their company, because of the type of problem that they're trying to solve and the type of systems that they're trying to build. Perhaps the main reason for the slowness in recognition of systems engineering as a career is the fact that it does not correspond to the traditional academic engineering disciplines. Most of the engineering disciplines are built on quantitative relationships, obeying established physical laws, and measure properties of physical material, energy, or information. However, that's not the case of systems engineering. We deal mainly with problems for which there is no or there is incomplete information, whose variables do not obey known equations, and where balance must be made among conflicting objectives involving incommensurable attributes. So again, we do not necessarily, within this discipline, we are not necessarily following the traditional disciplines in many aspects, because we deal with this uncertainty. Can I move to the next? I'll give you a couple minutes. Also, there are already universities that are changing the name of the programs, industrial engineering program, into systems. Systems engineering, or combining industrial and systems engineering. Also, there are computer science departments that are also um, including this discipline as part of their departments. So this is not just an area that is being um, gathered, or these concepts are not only used within the industrial or management areas, they're also part of computer science and other disciplines. Okay, so hopefully we will have the video, so if you are still needing to take some notes, you can refer to the video, and I'll put it in on our main page on the track site. So the establishment of systems engineering as a unique discipline has been inhibited by the absence of quantitative knowledge base. So you will see that during this semester that you will see a lot of exercises in which you're going to be drawing diagrams, or you are going to be performing some brainstorming exercises. There's a component of it that is math modeling, but there's no necessarily there's no formulas, there's no algorithms, there's no within this discipline. So the absence of those quantitative knowledge base is one of the things that had been against the discipline itself. Despite those obstacles, the recognized need for systems engineering in industry and government has spurred the establishment of a numeric academic programs offering master's degrees in systems engineering, mainly as a component of a part-time continuing education. A few universities offering undergraduate degrees in systems engineering as well. So there's also been a relatively recent recognition of systems engineering as a profession in the formation of a professional society, which is called the International Council on Systems Engineering. One of whose primary objectives is the promotion of this field in the education and the recognition of the area as a professional career. So if you want to learn more about that, you can, there's a webpage for this organization. So orientation of technical professions, again, the point that I'm trying to make with these following slides is that we are, as part of systems engineering, you need a balance in terms of the knowledge that you acquire. It's not science, pure science, it's not pure math, it's not pure engineering. It's a balance among these three areas. So scientists typically dedicated to understanding the nature of and behavior of the physical world, and they ask questions such as why and how. Mathematicians primarily concerned with deriving the logical consequences of a set of assumptions which are unrelated to the physical world. For example, if A happens, then B something. Engineers usually concerned with creating a useful product. So if we look at these three dimensions using this technical orientation phase diagram, you see that these three corners are addressing each one of the fields of science, mathematics, and at the top should be engineering. So when we try to find the technical orientation of systems, we are within in the middle, basically, that triangle. So we have combined knowledge from these three different areas of knowledge to try to address our problems. So what is the challenge of systems engineering? Systems engineering represents a deviation from a chosen established discipline to a more diverse, complicated, and uncertain profession practice. Requires investment of time and effort to an extensive broadening of the engineering base. So we are not just industrial, mechanical, electrical. We have to have some understanding of all these disciplines. Learning, communication, and management skills. I mentioned on the first lecture, there's some management components that are part of this discipline. A much different orientation from individuals' original professional choice. One may conclude that a career systems engineering is a difficult road, not obviously rewarding and altogether not very attractive. However, in a world that we are more connected, we are more access to data, that we see the need of having systems connected in terms of let's say, for example, Uber is addressing healthcare problems now by establishing a section of the business that is called Uber Health, that is looking at transporting patients that are non-emergency patients. So in a world that is looking at connecting these many areas, systems engineering knowledge is very useful. For a systems engineers, success is measured by the apparent absence of program difficulties rather than the spectacular successes. So making sure that you integrate everything, that's your success. Making sure that the complex system that you're proposing is working as expected. That's how you measure your success. Why do very good people devote their lives to systems engineering? The answer may lie in the challenges of the profession rather than the direct rewards. We deal with the most important issues in the system developmental process. They do not design the components, but do design the overall system architecture and the technical approach. So we need to set up what are the things that are required in terms of subsystems, for instance, in order to achieve that goal. And those are the assignments that we share with the rest of the disciplines. They prioritize the system requirement in conjunction with the customers to ensure that the different systems attributes are appropriately weighted when balancing the various technical efforts. So we have a direct contact with the customer. What are the ones who negotiate? What are the things that are required? What are the goals of the customer? What do they want to see at the end? What is the budget? What are the resources that they have available? What type of data can we gather from them? They decide which risks are worth undertaking and which are not, and how the former should be hedged to ensure program success. So this ties back to the case study that we discussed this morning. So what are the risks? Are you willing to take that risk of not testing the whole system together? How much will that cost you if it goes wrong? If that's something that you want to undertake or not. You want to make sure that you put that money into your testing, right? In that case. So is a systems engineer who maps out the course of the development program that prescribes the type and timing of tests and simulations to be performed along the way. So if you're an industrial engineer or you're in the industrial engineer program, we do simulations. I know you have to take a class in simulation, also the manufacturing engineer students. So those models become very important for understanding the performance of the system. So it's not just the test, but how those simulations are built and what are the things that they're looking at. There are the ultimate authorities on how the system performance and the system affordability goals may be achieved at the same time. So these two dimensions again, performance, affordability, and also the time are always important. How do you manage those three areas? Make sure that you achieve the goal by making sure that those are achieved. When unanticipated problems arise in the development program, it is the systems engineer who decides how they are going to be solved. So for instance, in this Hubble case, we saw that there were some problems. So what were the things that they decided to do and how to implement those? Those are part of the responsibilities of a systems engineer. So systems engineers derive their ability to guide the system development, not from their position in the organization, but from their superior knowledge of the system as a whole, its operational objectives, how all its parts work together, all the technical factors that go into its developmental or development, and the proven experience in steering complex programs through a maze of difficulties to a successful conclusion. So experience also play a major role here. If you have gone through the implementation of very complex systems, all those experiences build into your knowledge base, and you have more a better understanding of risk and how to deal with it. Okay, so how many slides do you have? Yeah, so we still have. So finally, the power of systems engineering. So systems engineering has a great influence over the design of the system, major characteristics, and the success or failure of the system developmental process. The influence comes from the systems engineering knowledge, skills, and attitude. So that last one is very important. You're going to be dealing with a lot of people, a lot of different disciplines. Not want to be generalizing, but for me, that there's some certain type of profiles for certain professions. So you have to make sure that you understand the way those, like for example, WE, they like to work more independent, individual on their station. So understanding those aspects of their profession and how to deal with those is very important. Multidisciplinary knowledge. So gathering that knowledge is important. So you know how to deal with their specific areas. Approximate calculation. Sometimes you don't have time to go and look for every single detail that might affect your computation. So how do you manage? How do you approximate forecast and make a judgment based on those numbers? And skeptical, positive thinking. So you're gonna go through some roadblocks. So how do you keep those that project moving forward? A successful system requires specialists in different disciplines, and we talk about that. So each specialist has its own language, foreign to non-specialists, and they have their knowledge base. So being familiar with those is important. Systems engineering provide the linkage that enable these disparate groups to function as a team. Okay, so that unification of these multidisciplinary areas and disciplines, that's where the job is, and how to make sure that everything is performed as expected so we can achieve the goal. Systems engineering requires the ability to make approximate calculations to ensure that critical omission or error has not been committed based on past experience, use first principles, apply basic relationships. And as I mentioned, you will see how we build some diagrams that will allow us to get to this relationship and cause and effect, and how these things are connected and how those help you to make decisions, and examine basic assumptions and conditions. Skeptical positive thinking. Skepticism is important to temper the traditional optimism of the design specialist, probability of success of a chosen design, insistence of validation of the approach selected at the earliest possible opportunity. So we have to keep a ground in terms of making sure that we are not too positive in terms of some of these designs, like for instance, avoiding testing, because we have a high a positive thinking that everything will go as expected. Positive thinking necessarily in reacting to failure of a selected technique or design approach, Many design specialists who encounter failure are plunged into despair. The systems engineer cannot afford to be in despair, need to find ways to circumvent the cause of the failure. So something happened, how can we fix it in the best way possible to move forward? Okay, so this is the last slide that we are gonna cover today. This is the last slide for the lecture. The next slides are just a couple of videos that you can look at on your own at home if you are interested. That shows some very complex systems. One of them is the airplane, the Boeing 777, and show you how everything that is involved in the design and the assembly of such difficult system. So any questions? So if there's no questions, then I'll see you on Monday next week.